Mark Rosengarten. Welcome to
Ask Rosengarten.
Hey guys, welcome back. Long time no see. Well, technically I'm on vacation now, but you've still got me. Actually, technically, LS Ampole 100's got me, to be specific. She says that she's got an issue with this particular question. Now, what we've got here is a medical problem. Calculate the dosage in milligrams per kilogram of body weight for a 135-pound adult. 135 pounds? Geez, I haven't seen 135 pounds since I was in like 10th grade. Who takes 2 aspirin tablets containing 0.324 grams of aspirin each. All right, well, let's work this through. We want milligrams of aspirin per kilogram of body weight. So our first job is to convert grams into milligrams, and that's easy enough. 0.324 grams, and there are 1,000 milligrams in a gram, because milli means 1,000th of. So to cancel out grams, we multiply and get 324 milligrams. So the total amount of aspirin consumed by this 135-pound person is 324 milligrams of aspirin. Now, actually consider 324 milligrams is a fairly large amount of aspirin, otherwise known as acetylsalicylic acid. Okay, that gives us the milligram part. Now we got to find the kilograms to divide by. Well, we've got a 135-pound person, but that's not going to do us any good because we need it in kilograms. And there are 2.2 pounds per kilogram. We want to cancel out pounds, so we have to divide. And that gives us, to 2 significant figures, 61 kilograms. So a 61 kilogram person who takes 324, that's 324 grams each. There's 2 aspirin tablets. I'm sorry about that. Well, we got to make sure that we multiply this by 2. That's a lot better. All right, 2 324 milligram aspirin tablets, 648 milligrams total. So we're going to take that 648 milligrams, we're going to divide it by the 61 kilograms of person that's taking it, and we get a total amount of 10.6, well, actually, there's 2 sig figs, so that would be 11 milligrams per kilogram of body weight for the person. So that's your dosage. The next question she asked me is, why is it possible for ships like tankers and cruise ships to float on seawater even though their hulls are built of steel, which comes from an iron alloy whose density is greater than that of water? Thank you so much. Well, if you put a piece of iron bar in water, the hydrogen bonds of the surface molecules of the water aren't going to be enough to prevent that iron bar from breaking through those surface attractions and sink to the bottom of your water. What's the difference between a bar of iron and a ship? A ship displaces a great amount of volume. When a ship displaces volume, it pushes water up around the sides. And you got to make sure that the sides of your boat are high enough to account for the mass of water that's being displaced. The mass of water being displaced gives you an upwards pressure on the bottom of the boat, and this keeps the boat afloat. So it's the volume of water that the boat displaces that keeps it floating on the surface of the water, even though the material it's made of may be denser than water. As long as the walls are high enough that it can displace enough water with its weight, you'll be able to get it to float. On the other hand, if the walls aren't high enough, as the water rises up, it'll just simply fill in, and there goes your flotation. Next question comes to me by Karen Addison. She's got 2 questions. She says, I have a question on isomers and homolysis. All I need to know is, what is homolysis and what are isomers? I know that isomers are the same molecules but arranged in different orders, but how do you recognize an isomer? Well, this is actually pretty easy. Now, this is just for simple isomers. I'm not getting into stereochemistry here or anything like that. I haven't seen it in like 26 years, so I'm not going near it. This is a molecule of ethane. Contains 2 carbons and 6 hydrogens. formula is C2H6. That's its molecular formula. This can be simplified to CH3, a 1:3 ratio, but for the purposes of what we're doing here, we don't need to do that. There is no other way to arrange these carbons and hydrogens to make a different molecule. So you could say that ethane has no other isomers. This is propane. It has 3 carbons and it has 8 hydrogens. There are no other ways to rearrange this molecule so that you could have a molecule other than propane. Now you might argue, well, what if I take this CH3, I'll move this H over here, and I'll put the CH3 over here. Won't that be a different molecule? Actually, it won't. Okay, an oversimplification is this. All of the bonds on a carbon are equivalent to each other. It doesn't matter where you bond it. In fact, technically, this would be the correct structure for this molecule because carbon forms tetrahedral bond arrangements. So what that means is I could have just as easily popped this carbon down here and it would have been exactly the same molecule. What you look for in an isomer is the number of carbons in the longest continuous unbroken chain, where you can attach carbon to carbon in one chain. So propane has no other isomers. This is butane. It has 4 carbons and it also has 10 hydrogens. Now we're starting to get somewhere. If I take this carbon and just put it up here, it'll still be 4 carbons in the longest continuous unbroken chain. However, if I took this hydrogen off, let's say here, and put the CH3 in its place, and then I put that H, I'll take that CH3 out of there, and I'll put the H there, now what do we have? We have 3 carbons in the longest continuous unbroken chain. Well, we could also say we have 3 carbons in the longest continuous unbroken chain. 3 carbons in the longest unbroken continuous chain. This is an isomer of butane. In fact, it's referred to as isobutane. The technical name would be methyl propane because it's propane with a single carbon dingly-dangly dangling off the dongle, a methyl group. The more carbons you have in your molecule, the more isomers you're going to be able to come up with. Here's another example. This is chloromethane. Now, I could put the chlorine here, 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 or here, and it's still chloromethane. This has no isomers. This is chloroethane. And again, it doesn't matter where I put the chlorine. The molecule is going to be the same. This chlorine could have been here, 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 or here. It's exactly the same molecule. If I put the chlorine here, that's like if I had taken this molecule, picked it up, turned it around, and shown it to you with the chlorine on the other end. Because molecules are 3-dimensional. You have to think 3-dimensionally. Now we're starting to get interesting. This is 1-chloropropane. Why 1-chloropropane? Well, the chlorine is bonded to the end carbon, a primary carbon, a carbon that is only directly bonded to one other carbon, in essence, a carbon on the end. So where else could we put this chlorine besides there? What about there? Well, it's still 1-chloropropane. So this is not an isomer of what we had before. The chlorine is still on the end carbon. It's as if I picked the original molecule up, turned it around, and showed it to you. On the other hand, now the chlorine is bonded to the secondary carbon, a carbon that's directly bonded to 2 other carbons, one on either side. What we have here is 2-chloropropane. That's an isomer. We had 1-chloropropane, this is 2-chloropropane. The fun gets even bigger when we start adding another chlorine to it. This is 1,1-dichloropropane. Are there any isomers? Sure. This is 1,2-dichloropropane. This is 1,3-dichloropropane. And this is 2,2-dichloropropane. So the more you have, the more atoms you have, the more different ways you have of rearranging them. But you have to take into consideration the fact that these molecules are 3-dimensional, and make sure you count the longest continuous unbroken chain of carbons. One more example. This is propene, 3 carbons with the double bond between the first and second carbons in the chain. This is also propene. The double bond is between the first and second carbons in the chain. Remember, Pick it up, turn it around, and look at it. This is butene. Butene and the bees. This is actually one butene because the double bond is between the first and second carbons. However, we have one isomer. Is that it? Nope, this is still one butene. The double bond is still between the first and second carbons in the molecule. So, where can we put it where it would be an isomer? There. This is 2-butene, where the double bond is between the second and third carbons in the chain. And the more carbons you have, the more places you'll have to put that double bond. Just remember to take a look and make sure that you've got one continuous unbroken chain and that molecules are three-dimensional. And the final question, what is homolysis? Now, I actually had to look this one up because I can't ever remember doing homolysis. But let's take a look at what the word means. We have homo, which means the same, and lysis, which means to loosen or to separate. Now, for example, in electrolysis, you separate a compound by the application of electricity. Electrolysis, if you will, using electricity to lyse or split apart a compound into its original elements. Using electricity, that's where the electro comes from. So to lyse basically means to split. So homolysis would be to take a molecule and through the application of energy, and most specifically light energy, and even more specifically ultraviolet radiation. For example, and a really simple example, there's one chlorine atom, and there's another chlorine atom. When you add light in the form of ultraviolet, those chlorine molecules will split equally. That's where the homo part of it comes into. That's homolysis. We have a molecule that's split with ultraviolet light, usually. And different molecules have different resonant frequencies that will cause the bond to break and separate evenly. That's something you would actually have to look up. So homolysis, taking a molecule and splitting it into equal parts using ultraviolet radiation to form free radicals. What a way to spend a vacation, answering questions for people out there. But you know what? To me, that is a vacation. So keep sending me your questions at askrosengarten@gmail.com. I'll get to them as soon as I can, and I'll do these videos. I'm going to try to get to them 2-3 times a week. So what are you waiting for?
Ask Rosengarten.